So now we're doing 9.16, and here we've been given the following block diagram that relates the input u with the output y, and there's a couple of states defined, x1 here, and then it should be one more, x2 down here. And what we're going to start to do here in task A is to find the state space form of the system using the state variables that we have here in the block diagram. So we have to find the relation between x1 and x2 and the input u and the output y. Okay, so let's start with this x1 because it's the easiest one. And if we look at this in the Laplace domain, we see that x1 of s is just equal to this transfer function, 1 on s plus 1 times the input u of s. And if we multiply both sides with s plus 1, we get s times x1 of s plus x1 of s, and on the right hand side we just have u of s. And then we're doing a inverse Laplace transformation of this expression. So the inverse of this is equal to what? Well, it's multiplication with s in the Laplace domain, which means that it's a derivative in the time domain. So this becomes x1 dot. And then we have plus x1. And this is equal to the input u. And if we solve this for x1 dot, we get that x1 dot is equal to minus x1 plus u. So that's our first state space equation. Now let's do the other one. So let's look at x2. So we see that x2 of s is equal to this transfer function, 1 on s plus 3, times the sum of x1 and u. So we have the sum of x1 of s and u of s, like that. And now we do the same thing here. So multiply this with s plus 3 in this case, since that's what we have in the denominator here. And that will give us s times x2 of s plus 3 x2 of s is equal to x1 of s plus u of s, like that. And now we're doing an inverse Laplace transformation of that. So just as before, this one becomes x2 dot when we have multiplication with s here. So it's a derivative in the time domain, and then we have plus 3 x2, and this is equal to x1 plus u. And if we solve this for x2 dot, we have that this is equal to x1 minus 3x2 plus u. And then finally we see from this block diagram that y, the output, is just the sum of these two states. So y is equal to x1 plus x2. So let me write that down here. So also y is equal to x1 plus x2. So now we can set up the state space matrices. So let us do that here. Can we keep this? Maybe like that. Okay, so we have x1 dot and x2 dot is equal to what? Something times x1, x2. And then these elements in the A matrix is just obtained by looking at the relations we found. So x1 dot is equal to minus x1, so we have a minus 1 there. And we have no x2, so it's 0. And then we have plus u, so plus 1 times u. And for x2, we have x2 dot is equal to x1 minus 3x2, and then plus u. So this b vector is 1, 1. And then finally we have that y is equal to the sum of x1 and x2. So it will be 1, 1 times x1, x2. And this is the vector that we usually call x dot. And this one is then, of course, just x. And this matrix is our A matrix, and this is our B vector, and here we have the C vector. So this is the state space form of this block diagram. Cool. Now we're going to move on to exercise B. Let's see. That. So what are we going to do here? We're going to compute a state feedback. Such that what? That puts, I'm just writing the instructions from the exercise, that puts the poles of the closed loop system closed loop system in -4, and that gives a static gain equal to 1. So static gain of 1. That's the exercise. So if you think of this in terms of the closed loop transfer function GC of S, what these requirements are saying is that we should have both the poles of this transfer function should be in -4. So this will be of the form S plus 4 squared. That will be the pole polynomial, since now we have two poles in -4. And then we'll have something up here in the numerator that is determined by the system matrices that we have in this state space model. And then static gain of 1 means that GC of 0 should be equal to 1, like that. So in order to obtain this, we're using state feedback. That means that we're choosing the input signal U as a linear combination of the states x1 and x2. And the convention is to do that in the following way. So we have minus L1 times x1, and then minus L2 times x2, plus L naught times some reference signal R. And then we write this like minus L times x plus L naught times R, where this L is just L1 and L2 concatenated in a vector, in a row vector. So we need to determine this L with the coefficients L1 and L2, such that these properties are obtained. Okay, so let's see what this implies. Get rid of that one. So if we look at the state space equation that we had, so we have x dot is equal to a x plus b u, right? What will this become now? Well, we'll let u be equal to minus L times x plus L naught times R. We'll substitute that, so that will give us ax plus b times minus Lx plus L naught R. And this is equal to ax minus blx plus L naught R, which is a minus bl times x plus L naught r. So this will be the governing equation when we're using this feedback. And since we wanted to use L to control the placement of the poles of this closed loop system, we have to look at the pole polynomial. And the pole polynomial is given by the determinant of what? The determinant of S times I minus this system matrix A minus BL. So it's minus A plus BL. That will be the pole polynomial. And if you have forgotten why that's the case, you will see that later in the exercise when we form the closed form transfer function from this expression. Okay, let's calculate this thing. So let's put some brackets here. So we have the determinant of Si, which is just SS and then 0, 0, S times the identity matrix, minus A, and A was what? It was minus 1, 0, 1, and minus 3. And then plus BL, and B was just equal to 1, 1. And then we have L, which is L1 and L2. Okay, like that. Okay. So let's do this one here. So we have S minus minus 1, which is S plus 1. And then we have 0 minus 0, which is 0. 0 minus 1, which is minus 1. And then S minus minus 3, which is S plus 3. Plus this thing. So 1 times this vector is just the same thing. So we have L1 and L2. And here as well. Oops. L1, L2. Okay, and then we just add these up. So it's the determinant of S plus 1 plus L1. And then we have 0 plus L2, minus 1 plus L1, which is L1 minus 1, and S plus 3 plus L2. S plus 3 plus L2. Now we're taking the determinant of this, which is the product of the diagonal elements minus the product of the anti-diagonal elements. So it's equal to S plus 1 plus L1 times S plus 3 plus L2. And then minus L2 times L1 minus 1. Alright, so let's expand this expression. Let me see. So we have oops. We have what? We have S squared plus 3S plus L2S. I'm doing this term by term now to make sure I'm getting the correct thing. And then we have plus 1 times S, S plus 1 times 3, 3 plus L2. And then plus L1 times S plus 3L1 plus L1 times L2. And then minus L2 times L1. And then minus L2 times minus 1, which is plus L2. So what do we get? We get S squared plus something times S. We have 3, we have L2, and we have 1, and we have L1. And then we have the constant terms, which are 3 plus L2 L2 plus 3 times L1 plus L1 times L2 minus L2 times L1. So this thing cancels out, it's equal to 0. And then we have plus L2 over here. So if we simplify this one more time, we get 3 plus 1, which is 4, plus L1 plus L2 here, times S, and then plus 3 plus 3L1, and then plus 2L2, but since we have L2 there and there, so plus 2L2. Alright, so what we have to do next is to compare this with the desired pole polynomial. So compare with the desired one, which was what? Well, it was this, since we wanted both the poles in -4. So if we expand this, we get s squared plus 2 times 4, 8s plus 4 squared, which is 16. And now we're comparing this with that in order to identify the coefficients. So we get an equation system. So this thing must be the same as 8. So 4 plus L1 plus L2 should equal 8. And then the constant term should be equal to 16. So 3 plus 3 L1 plus 2 L2 should be equal to 16. So this is the equation system that we have to solve. And if we look at this first equation, we can solve this for L2, for instance, and then we see that L2 is equal to 8 minus 4, which is 4, minus L1, like that. And then we plug this into this second equation, which gives us 3 plus 3L1 plus 2 times L2, which is 4 minus L1, must be equal to 16. And what does this imply? Let's just solve for all the terms on this side. We have 3 plus 3L1 plus 8 minus 2 times L1 equal to 16. And we see that if we keep all the L1s on this side, we have 3 minus 2, which is 1, L1, is equal to 16 minus 8 minus 3, which is 5. So L1 is equal to 5. And by plugging that into this expression for L2, we get that L2 is equal to 4 minus 5, which is minus 1. So this L vector becomes 5 minus 1. Now the next thing we're going to do is to ensure that we get the static gain of 1. And in order to do so, we're going to consider the transfer function. So recall that we had the following state space a minus bl times x plus bl naught times r, like that. So if we do a Laplace transformation here, solve for y, we'll find that the transfer function is given by this expression. You can derive that if you want to, just Laplace transform both sides, solve for x, and then multiply with c. That will give you y as a function of r here. And that's going to end up with the following expression. So it's c times si minus a plus bl inverse times bl naught, and then this r. Oh, sorry. That is not a part of the transfer function, of course. It's just a reference signal. Alright, so let's calculate this thing. We know that one already. Si minus a plus bl. And we found that this was equal to S plus 1 plus L1, and then L2, L1 minus 1, and S plus 3 plus L2. And now we're plugging in the values of L1 and L2 that we found. So L1 is equal to 5, right? So this becomes S plus 6, and L2 was minus 1. So this is 4, and this is S plus 3 minus 1, S plus 2. And now we need to take the inverse of this matrix, Si minus A plus BL inverse, which is the inverse of this one. And before I write it out, let us just remember that the inverse is equal to 1 on the determinant of the matrix you want to invert. So it's Si minus A plus BL. The determinant of that times the adjugate matrix, which we denote like this, adjugate. Sometimes it's also denoted with a star. It's not a complete consistent notation. Anyway, you see here that the determinant of Si minus A plus BL is down here in the denominator. That's why this is giving us the pole polynomial. So we used this expression earlier to form the expression for the pole polynomial, and this is the explanation. Okay. So let's calculate this. The determinant of this expression is S plus 6 times S plus 2, and then minus 1 times 4, so it's minus 4, so plus 4. And then the adjugate of a 2 by 2 matrix is obtained if we just swap the positions of the diagonal elements and multiply the anti-diagonal elements with minus 1. So we'll get 1 here and minus 4 here. Like that. And now we can plug this back into the expression we had up here. So GC of S becomes C, and C was equal to what? C was equal to 1, 1. Times this thing, 1, and of course if we simplify this expression here, we'll get the pole polynomial that we wanted. And here we have the same thing, and then times the B matrix, and the B matrix was equal to 1, 1. Alright, so do we say it now? Yeah. So this is equal to what? I'm gonna move that up front. 8s. And then we have 1, 1 times this product. Let's do that one. So it's S plus 2 plus 1. And down here it's 1 times minus 4 plus S plus 6. And this becomes what? This is the same thing. S plus 8, S plus 16. And then we have the sum of this. So it's 1 times S plus 2 plus 1, S plus 2 plus 1, and then it's minus 4 plus S plus 6, which is equal to what? Well, 2 plus 1 is 3, minus 4, that's minus 1, and then plus 6, that's 5, and then we have S plus S, so it's 2S plus 5 on S plus 8, S plus 16. And now I just realized that I forgot this L note thing. That one. That should have been included here. L note. And then of course also here. And here. And then here. So this is the transfer function, GC of S. And then we required that the static gain should be equal to 1. Which was the same thing, that GC of 0 should be equal to 1. So, if we look at that, what do we get? Well, we get 5 in the numerator, and we get 16 in the denominator, times L naught. And if we required this should be equal to 1, we get that L naught must be equal to 16 on 5, which is 3.2. So the final transfer function becomes 3.2 times this thing, 2s plus 5 on s squared. Sorry for that, forgot it everywhere. S squared plus 8s plus 16. Okay, so I think that's it. Yes.